happy to have a Spencer from our own department to tell us QKZ.
Something about QKZ, okay. Yeah, thank you for inviting me to do this. So yeah, the talk today is going to be like, somehow much lower level of generality than some of the other talks. But it'll be sort of how you can see like the first steps towards the categorification. And I hope this will like serve as some motivation. This stuff is interesting. So kind of two things that we hear about this year are like the not invariants and their categorification. And then also stuff with geometric length. So I will probably focus today mostly on the first thing and say like a couple of words about the second thing, but not too much, hopefully. So if you're a physicist, you know that these two kind of share a common character that appears, and this would be like current algebra or WZW conformal blocks. And kind of subset of these are things that solve KZ equation. So I'm going to start with kind of reminding why this is the case, at least in this story. And this hopefully will give you some reason to care about KZ equations so that I can explain better and better ways to solve them. Oh, what is the geometric-Langlands connection? So if you study, well, it'll be partially clarified when I explain the first thing in some detail, but conformal blocks, when you formulate them mathematically, it can be regarded as objects which can live over Bun G if you have some kind of current algebra symmetry. And in favorable cases like WCW model at critical level, sometimes they're correspond with Heck eigenschafts. Okay. So basically in knot theory context, if you think about Chern-Simons, this usually, you need to have gauge group G. Probably in the beginning, I'll say stuff that's fine for general G, but most of what I'll say today will be okay for SU2. You pick some level K, which is integer. And you should be on some 3 manifold, but since we're just having some general discussion, I'll just say S3 because I want to focus on knots. And Chern-Simons action, it's a usual thing. And the claim, going back to Witten many years ago, is that if you look at expectation values of Wilson lines in Chern-Simons theory, these are going to give you some kind of not invariance, where the Wilson lines, basically the traces of the holonomies of the gauge field along the knot. And R is some representation of G, and Q is exponential of 2 pi I over kappa, where kappa is this level plus some one loop shift. Okay, so this is hopefully something people know. To see where conformal blocks and KZ equation enters the story, basically you just ask, how do you actually calculate expectation value of Wilson line from a physics point of view? And what kind of Witten teaches you is that do this by cut and glue. So if you've got some knot and you have the local piece of it, which looks like braid, and I'm not going to try to draw anything complicated, so I'll just draw something like this. Basically, you pick a time direction, and you cut open along spatial slice. And in principle, this could really be part of like a link. So these could all be coming from different sort of connected components, and you get punctures on your spatial slice labeled by representations of gauge group. So spatial slice I'll call A, and the point of one of the main points of Witten's paper on this is that the Hilbert space that you get on A from canonically quantizing Chern-Simons is space of conformal blocks. In WCW, where there are various like identifications you should make based on gauge group level and representations. So at the risk of belaboring it a little bit, but to explain why I wrote number 2, I'll briefly recall how this goes. So for this discussion, you want to do the canonical quantization. And for here, forget punctures for a second. You can just think of A as some completely general thing. So if you want to canonically quantize on A, usually you do this. So the nicest way to do this is the geometric quantization, which means that you make your wave function just a holomorphic function of AZ bar, or AZ bar is the 0, 1 component of gauge field. A along curly A. And obviously, to write this formula, I've had to pick some complex structure on my Riemann surface. Okay. Now, because you're doing gauge theory, you can't just say, naive quantization. You have to say what to do about gauge invariance. And the transformation, which comes from Gauss' law and Chern-Simons theory, is that if you make gauge transformation of this thing, you get some transformation, you get some prefactor, which is like exponential of WCW model action plus trace of AZ bar with DGG inverse and some psi. And what I've just written here as equation, this is the same as saying that psi is a global section of some line bundle over the moduli space of semi-stable holomorphic GC bundles on A. Semi-stable, you have to be somewhat careful about this thing coming from real moment map. But point is, this is like finite dimensional compact space. And so, you get finite dimensional Hilbert space of Chern-Simons theory, which is responsible for many simplifications. Okay. So if you're a mathematician, you can take this more or less a definition of WCW conformal blocks. Line bundle is sometimes called equivalent determinant bundle. Okay, so why do we care? This setup kind of gives a geometric explanation for existence of things like KZ equation, because the idea is that the Chern-Simons theory is topological in 3 dimensions. So you expect that it actually has, in some sense, an independence on the complex structure that you picked on Riemann surface in order to carry out geometric quantization. And the precise way that this sort of shows up is that this thing varies as the fiber of a vector bundle over the moduli of complex structures on your spatial slice. And the vector bundle turns out to carry a flat connection, which is sometimes called KZB connection. And then KZ equation and its generalizations in higher genus just basically say that wave functions are actually parallel under this flat connection. Okay. So as the picture suggests, for knots, you actually care about genus 0 with punctures. So when A is something of genus 0, and you have some punctures. So just again, completely generally, you can think of it like this. Pretty soon we'll want to think of it as cylinder. The conformal blocks have pretty simple description. So remember, these are really labeled by representations in Chern-Simons theory. the blocks are just valued in space of G invariants, and they solve the equation which looks like kappa TDAI, and sum over the J's. Where this thing is just constructed out of some Lie algebra generators, which are normalized. And A and B are Lie algebra indices. So this is called KZ equation. And then unfortunately, I think I hid or erased it, but you know, to compute the not invariance, you just do the most naive possible thing that you could given the picture. You just, if you have some braid describing points moving around each other, you just analytically continue solutions to KZ equation along path corresponding to the braid. And then the monodromy of KZ controls actually the not invariance. Okay. So one more thing I should mention is that the KZ equation in some sense follows from this affine Lie algebra symmetry at level kappa. Basically, well, this formula here, if you write psi in the form of like the expectation value in some two-dimensional theory that lives on A of the trace of some current paired with AZ bar, and you expand this out to second order in G for G near 1, it'll give you the usual like current algebra awarded empty for WZ. Okay. Great. So the thing is that from this point of view, it's not at all obvious that not invariants have any kind of nice categorification. I've just said, okay, take some solutions, some equation, analytically continue them. You know, who cares? But the very existence of the categorification suggests that maybe there's something else going on with KZ equation. And this actually becomes even more pronounced when you start asking about things you can do with KZ equation, and if they make sense in Chern-Simons theory, or how complicated they are in Chern-Simons theory. Because something which is kind of obvious from just the form is that you don't need kappa to satisfy any constraint. Kappa can be complex. And the equation's still good and the solution still makes sense. So you can go to complex kappa. But in Chern-Simons theory, of course, if kappa is not integer, gauge invariance is broken. So you need to actually analytically continue in Chern-Simons, and already doing this, some kind of complicated story. And moreover, the equation is clearly written just in terms of Lie algebra generators. Okay. Whereas in order for Wilson lines to make sense, you really need these to be representations of group. Okay. But KZ equation makes sense even if these are representations of Lie algebra, which don't exponentiate to representations of group. So in particular, you can consider it for, and now we'll just do SL2 because anything else will be just unnecessarily complicated. Some kind of Verma module where the highest weight is some kind of generic complex number. Okay. So you can ask, you know, the KZ equation and its solution still makes sense in this scenario. And you can ask actually, what does this correspond to in Chern-Simons theory? I already said you had to analytically continue. And for the Verma modules, what it turns out is if you have your not K, you should look at the analytically continued Chern-Simons theory on S3 with K deleted. And what you impose is that if you have, so we could imagine K actually to be a link with like many components. If you have some component of K and it has a like loop linking it, what you do is in path integral of Chern-Simons, you impose that the holonomies of the gauge field around the small loops linking the components of K should be in the same conjugacy class as this thing. And so this is a pretty complicated thing to do in Chern-Simons theory. Okay. However, there's sort of a proposal or expectation for what its partition function should compute in such a situation. It was studied by Gukov and Manolescu. They called this thing FK of Q and X. And so here you just assume you have one component, so there's one variable x, which is basically q. And so morally speaking, what this thing is, as sort of its origin suggests, is it's like roughly an analytic continuation of colored Jones polynomial. But this is sort of difficult to make precise, at least naively, because what you're analytically continuing in is number of colors. Or sorry, yeah, just the weight of representation. And these are, of course, infinite dimensional, and so there's all kind of subtlety that goes into defining this. It's going to be some kind of two-variable series. Okay. Now, people expect that there should be some kind of categorification of this series, and hopefully I'll say something about this at the end of today. But clearly, trying to approach that from bulk Chern-Simons' point of view, pretty complicated. What would be desirable is to have some kind of approach to categorification, which plays nicely with KZ equation. More precisely, to specifically categorify solutions in KZ equation. Okay. Because then everything just uplifts directly, and you can use the more simplified story. Okay. So this is hopefully what I'll tell you how to do today. And of course, the other thing is, like, from physics point of view, you want to think about not categorification, not just for its own sake, but because the existence of the categorification is supposed to teach you something interesting about behavior of quantum field theory and string theory and so on. Like, the interest of the not invariance in Chern-Simons theory at first for physicists was really that you learn things about Chern-Simons theory. So we want some approach to this which is also rooted in physics. And so to get the nicest possible story, it turns out to be convenient to sort of deform the problem. So I mentioned we had this kind of affine Lie algebra symmetry underlies KZ equation. And this admits a deformation, something called a quantum affine algebra. Okay. And KZ equation correspondingly deforms into a Q difference equation called the QKZ equation. Explicit form of QKZ, if I write it in general, the whole operator will take up the board, but I'll write some special case of it in a second. An important thing is that actually the Q deformation actually spoils the conformal invariance. So the universal enveloping of this thing contains Virasoro algebra. This is not true here. You know, previously I was thinking about KZ on just like punctured sphere or something, and here we really want the surface to be flat. So QKZ is most naturally happening on like a cylinder. So this is now A. There are some punctures here, which you can think of in the middle. And then at the end, you can attach some states like lambda and lambda. And for me, everybody's going to be Verma module. So we have vertex operators at punctures corresponding to the Verma modules with some generic complex highest weights. And the solutions, or the functions that QKZ acts on, are naturally valued in a tensor product. The n Verma modules in the middle, and you restrict to the subspace of weight. Well, in general, lambda prime minus lambda, but I'm going to impose that lambda prime minus lambda is actually sum over alpha is new alpha minus 2k, or k is now a negative integer. And so you restrict to this weight subspace. And so, for example, for n equals 2, what QKZ looks like is if you have psi of QA1, A2, you should get something like z to the rho, and so 1, R1, 2, A1 over A2, and psi of A1, QA2. Where now R's are Important thing being that they're the R matrices. And for me, of UH bar SL2 hat, where these are Verma modules. So a lot of writing, but this is just the Q difference upgrade of KZ equation. Okay. And the point is that it's much more natural in the Q world to search for sort of upliftings of this structure. And this has to do with existence of, this in some sense corresponds to working with 6-dimensional 2,0 superconformal field theory. And this has a deformation to something called little string theory, which is what QKZ naturally lives in. I'm going to try to decouple all of that from today to just tell some kind of mathematical story. But there's some reason why this is simpler. A kind of more down-to-earth way to say what the approach is that there's an insight going back to Nekrasov and Chadashvili that these kind of quantum affine algebra symmetries should be realized in our case in 3-dimensional n equals 2 supersymmetric gauge theories. And so the idea, and in softly broken n equals 4 case, many of you are familiar with this, is that you can get this kind of symmetry is coming from usually like action by correspondences on some algebraic varieties. And quantities of interest in gauge theory can usually by supersymmetric localization be translated to some questions, well-defined questions in algebraic geometry. Okay, so today I'm going to tell you about the well-defined reduction of this to algebraic geometry. Okay, something else I want to emphasize is that it's actually very important that you really need n equals 2 for what I'm going to say today. So again, most work in the kind of direction that I'm going to talk about today is for n equals 4 gauge theories, which means in math that you're studying Nakajima quiver varieties. The thing I'm going to study today is not a Nakajima variety. Okay, I'll explain what it is in some depth, but it's not a Nakajima variety. But the important thing is that we still get some kind of structure, which allows us to produce solutions to QKZ equation and quantum affine algebra symmetry from geometry of this space. Okay. So maybe I'll. Yeah.
So what is there is Q-first equation.
Yeah, I mean, in principle, you can try to solve it directly as an equation. I mean, people did this in like 90s. But the point is, if you want to try to uplift anything, you want to have some geometric interpretation of what you're doing, or gauge theoretic interpretation of what you're doing, because. Yeah, I think probably in any kind of like basically as long as your Lie algebra is like classical type, like finite and ADE, probably this was covered somewhere in either 90s research or like old special functions book or something. Only GLN? Oh, okay. So well, at least everything I'm going to say will fall into that example. So yeah, no, the actual like integral formulas are in GLN go back to people did that by brute force, but yeah.
The very first paper was because it is integrated the also
Yeah, and in some sense today I'm just going to tell you the modern reformulation of that statement. Right, but the point is that this all places it in some broader geometric context, and it also, when it's brought into the world of like the modern physics of supersymmetric gauge theories, this really tells you much more structure than might have been observed just by staring at the formulas. So the point. Everything we say today is good enough to write down formula. So, oh, this is the other thing. So yeah, yeah. No, not. Yeah, no. The claim is absolutely not. No, general n equals 2 has almost no hope of working. In fact, I'm still trying to think what is the, correct way to state at what level of generality you expect this to work. I'm just going to tell you some class examples where it definitely. No, general n equals 2. Yeah, so I should clarify that general n equals 2 is definitely asking too much. You're gonna that's no, but just some n equals 2. Yes. Okay. Yeah, somehow. Right.
So, well, I think what probably shows that if you have to have that before that, really think it really a lot of functions. I think that's okay. Not quite that. No, but I mean, you need to quantify something. Well, we'll get there.
Yeah. So we'll get. Yeah. So let me tell you. I'll explain some of those words. The way that you actually get the solutions is you look at kind of generating function. Of some curve counts. And they usually look like maybe you got P1. And this gets mapped in some space, which for me, it'll be labeled by 2 integers, and the integers just correspond to basically the number of punctures on A and the weight subspace that you're in. Okay. And the important thing is that all parameters of QKZ become sort of, so this includes like the positions of the punctures, the highest weights of Vermas, H bar, Q, they all acquire some geometric meaning. They're related to torus action. Now, kind of the main character of today is this XKN, because set up like this is very, very well studied, in which in the case where X is some kind of Nakajima core variety. For me, it'll be something else. One way to say is it's the moduli space of degree K quasimaps, which go from P1 into well, here, so I'll write cotangent bundle of Grassmannian n, 2n, and they're sort of based at infinity. This just means that you send infinity in some kind of, they're somehow trivialized here. You send some prescribed point. So of course, so if you, I'm not really going to explain technical definition of quasimap in talk, but if you've never seen this, you can just think of these as it's some kind of compactification of the naive space of holomorphic maps. But the important thing is that, like, if you have a holomorphic map into T star Grassmannian, it's of course redundant to write T star Grassmannian. They're all going to land in the Grassmannian. But the reason I write this is because I want to think of this as like A1 Nakajima variety. So everything I'm going to say today will be for A1, but there's some generalization that should work if you replace this by ADE. And so in physics, this just means it's going to be some kind of partition function of supersymmetric gauge theory. The important thing, which makes things actually work, is that, and related to the fact that you actually have some gauge theory description, is that XKN has a quiver description. So to describe the quiver, I'll fix 2 n-dimensional complex vector spaces. I'll just call them m plus minus. There will also be some k-dimensional guy.
if you want to this next data, the data itself is all the perfect maps.
Yeah. So this suggests that the problem has natural origin in complex dimension 2. And it does, but I'll I want to try to guess what it is, and then eventually I'll say what it is. And the quiver is really simple. It's just this thing. All the arrows B, I, and J. So you just take the space of B, I, and J, which sit inside of endomorphisms of K, plus Holmes from M plus into K, plus Holmes from K into M minus, just as the picture suggests, and then you impose some stability condition, which explicitly says this. And then you divide by yeah, okay. So I'm running out of room, but so that's the space. Great. Now, in order to actually get to QKZ equation, I'm going to need some group action on the space. So I'll explain a little bit about what this looks like now. This will be also important to see why it's able to describe these Verma modules. Yeah, GIT quotient. So this is just a stability condition. I just wrote it explicitly. The other thing is that I should maybe I'll say a couple of words. Like to physicists, I think these type of quiver descriptions of quasimap spaces are pretty familiar because they follow immediately from sort of brain constructions and go back to works of like Hanani and Tong. In math, I don't know how common they are. There's a paper of Nakajima about handsaw quiver varieties, which explains this. This is the simplest case of that. But at some more conceptual level, it does follow from ADHM description of instantons. Okay. And just to say it, I will not use this, so I won't explain this in any level of detail, but to say in words what the correspondence is, it's an old theorem of Atiyah that you can think of instantons as sort of like holomorphic maps to affine Grassmannian. So this sort of, instantons live in C2. So if you break up C2 into like C plus C, you can sort of think one direction becomes like the loop part of affine Grassmannian, the other direction is the base curve. And then if you take C star fixed points inside of there, you can get maps to finite flag varieties and those type of quivers from ADHL. Okay, so group action. From the quiver, it's clear that you get action of GL M plus times GL M minus times C star H bar. In Grassmannian, in the moduli space description, these two actions come from group acting on Grassmannian that preserves the base point. And this action just corresponds to scaling the base P1. In the quiver description, this is like scaling B. And so I'll write equivariant parameters associated to these guys, which in physics, these are the twisted masses in 3D n equals 2, which will be, I'll just call them M alpha plus, M alpha minus, and H bar, where alpha is index that runs from 1 to n. And you think of these as being associated to maximal torus inside of here. Yeah, just by changing, just by natural action here, because it's vector space. Just GLN. Yeah. So but Grassmannian has GL2n action.
Yes.
Okay. Now, if I fix a base point, the action preserving that point is GLN times GLN. And so that's this. Yeah. So the M alphas are related to the parameters that enter QKZ directly by some kind of thing like this. So basically the splitting between them determines the highest weights of Verma modules. Okay. And you know, from physics, the A's, which determine the positions of the vertex operators, would correspond to the like n equals 4 type masses, where if you wanted to preserve some kind of n equals 4 supersymmetry, which doesn't exist here to begin with, you would have turned on twisted masses like that. Okay. And so associated to this, you get a kind of distinguished subtorus, A in here, which corresponds to the C star n diagonal side of the GLM. Okay. And this will be important later for stable M. Okay. So the unfortunate thing is, you know, for Nakajima varieties, all this stuff is like very well known and push all the combinatorics under the rug. But to explain actually the correspondence intelligibly, I'll have to tell you a little bit about like what the fixed points look like. I'll just tell you how to label them. So the fixed points correspond with, you can just think of them as n tuples of integers. Like K1 through Kn, which satisfy K is. Okay, so sort of pictorially, a way to think about it is if you sort of pick some, if you think of the real masses in gauge theory, put them on real line, pick some ordering. And what the fixed points look like is basically just you know, dots and bins. And so the important thing is that this is obviously just in bijection with how you apply lowering operators to SL2 Verma module if you have a tensor product of n of them. Because if you're in weight K subspace, that means you have to have lowered the total weight by you know, something like K. And so each time you apply a lowering operator, you lower the weight. And if you have n of these, you can do this in all possible ways. Okay. Yeah, so the each fixed point corresponds to one picture like this. So like if I had the one where all K are on n, that would be one fixed point. Then I could have one where K minus one of them are on n and one of them's on one, and then I would draw K minus one things here and one thing there. So, yeah. Yeah. So eventually, oh, right. I skipped like most important thing. As experience from, you know, for people that know Nakajima's story, what you want is the T equivariant K theory of this thing. And so to write, for what I'm going to say to be literally true, you need to like tensor. You need to just like restrict equivariant parameters to be kind of something generic. This will correspond actually to the space on which the QKZ operators act. And so what I'm saying is just if I'm interested in this thing as a vector space, it's good enough just to know its dimension. And what I'm saying is that the basis elements of here, which come from applying lowering operators, are just in one-to-one correspondence with fixed points in here if you view them this way. Yeah. Well, in some sense, yeah, you think of these as actually like very close together. And then, yeah. Yeah, exactly. Yeah, exactly. Okay. Yeah, like if you wanted to draw it just in terms of A's, you would like maybe stack them on each other. But like the point is the small separation, they sort of fill it in. Okay. Yeah. So like if this was actually T star Grassmannian Kn, the point is you would be forced to stop lowering after one step. So you would just have single dots over single points. But here you can just keep going. Okay. Great. So that's the structure of the fixed point. Oh yeah, sure. Yeah. Okay. Thank you. I see. Sure. Okay, great. All right. So that's the space. This is sort of basic information about it. Now I'll tell you a little bit about what curve counts look like. And this also will be where complex dimension 2 sort of emerges. It's more like Gromov-Witten curve count. Yeah. But I'll say what it is now. Actually, I forgot exactly which way I'm going to formulate this. Yeah. Okay. Right. So, again, physically, what the curve count is some kind of supersymmetric partition function. So, really, you should think of it as kind of vector valued, more or less in this space. And that corresponds to kind of choice of vacuum at infinity, or the vacuum is just kind of fixed point. To sort of keep things so that I only have to explain one thing at a time, I'm just going to extract a particular component of the vector corresponding to a particular fixed point. So I'm going to just pick some fixed point. And then I'll tell you what the quasimap counts I want to do look like. So I'll call this the partition function. It's going to depend on like all parameters, including a new one that I'll define shortly, but this also appeared in QKZ equation. So again, now I had defined X as some moduli of maps. Now you look at maps into X. I said in the beginning, and you just require them to approach P at infinity. And you work equivariantly with respect to all symmetries of the problem, which means like in physics language, you turn on the omega background corresponding to rotation of base P1. And great. And so this just means the state F of infinity is P. So you call I'll call the corresponding moduli space QMP of, and then I'll also single out the degree. So again, I'm being sort of intentionally vague about definition of quasimap just to avoid getting bogged down in detail. But there's some notion of degree, and you select degree D. So what you want to do is, again, I said work equivariantly with respect to all symmetries of problem. That means that you think about a torus acting on this, where T was maximal torus from there. So that's just all those symmetries. And then now in addition, the symmetry rotating base curve. Yes. So this has rank 2n plus 2. It's easy to remember because every variable has like a partner in some sense. And what you want to, so a quasimap, this is a moduli space of quasimaps, which is some way to compactify naive moduli space of curves. And in it, there's a distinguished, well, in its K theory, there's a distinguished class called symmetrized virtual structure sheaf, which comes from the obstruction theory, perfect obstruction theory that quasimaps have automatically. And more or less, this thing is just the naive virtual structure sheaf, which comes from the obstruction theory, tensored with the square root of the virtual canonical. And then really, okay, so there's like one more thing, but it doesn't really do anything. Okay, and then your partition function is now a sum over all degrees. Little z is a degree counting parameter. Maybe I should. It's a FI parameter in physics language. And what you're doing is you're looking at the T times C star Q equivariant Euler character of symmetrized virtual structure sheaf on this thing. And you can just explicitly compute this by localization. Okay. Now, I will not explain to you the full localization formula for this thing, but I'll tell you what the fixed points inside the quasimap space look like. Maybe I will. Yeah, I think I can use this still. So fixed points in quasimaps. Now, instead of corresponding to integers like this, when you do these kind of problems, you should always think of integers as partitions that can just grow one direction. So the fixed points in quasimaps, partitions can just grow this way on top of these ones.
The reason I thought this picture on the lines is that
I mean, this is also kind of a combinatorial picture. I'm just telling you which points to sum over. No, it has some meaning. Yeah, there is some cutoff. Yeah, these can't be arbitrary size. I mean, so somehow the actual precise statement is the partitions. You get n tuples of partitions, lambda alpha, such that their lengths are at most these k alphas, which corresponded to the original choice of fixed point in X. And if you're in degree D, then basically D is the sum of it's the total number of boxes. Oh, okay. Oh, okay. Yeah. Let me. Yeah, maybe I didn't draw this super faithfully. But the point is that so for these you want to just do the minimal tuning, and the minimal tuning will only enforce this. Okay. But what you're saying is correct, right? That's how you would go from like tuning parameters in this back to Grassmann, right? And so now, if you've got something that has a natural origin in complex dimension 2, its localization formula comes sum of partitions. I think probably people in the audience can guess what it is. This thing will actually just be Nekrasov partition function. Of 5D n equals 1 theory with this quiver. So that's UN with 2n fundamental hypers. And then the tunings by K's here corresponding to at restricted Coulomb moduli. And so physically, in some sense, I'm telling the story backwards. Physically, you somehow start here and arrive at this. But here, just from geometric point of view, you can climb back up. Okay. So the point of yeah.
So this picture itself, it labels fixed points.
In my setting, fixed points of this on this. Okay.
But in real line, it feels like the actual, that's the one that I know about.
Mm-hmm.
Because this story is about invaders, I guess, it's not including or something a while, and I'm not sure. So, I don't know.
Yeah, yeah. It's like discrete. Yeah, yeah. So the Q, that's the effect of Q deformation, basically. Yeah, yeah. So right.
So to have some overall possible partition.
Yeah. Sum over all partition. That's what the localization sum looks like. Yeah. When you compute this by localization, you find the sum of a bunch of terms in degree D. Each one of them corresponds to a partition, collection of partitions of this type, and you can write some formula for the localization measure, which I will not subject you to, but is actually not that bad.
But this is not the final answer.
No, this is not the final answer yet, because I said I was going to somehow get back to QKZ. The point of what I've said so far is just to convince you that this space is actually interesting and connects with sort of known objects. So for QKZ, you need one more step, which I'll explain here. It has to do with the fact that you actually need something for QKZ operator to act on. This corresponds to a particular operator insertion in this theory here. So you want to make an operator insertion. And so your choices basically come from chiral ring of 3D n equals 2 theory, and it's pretty well known that that will also correspond, at least as a vector space, to equivariant K theory of the variety. I don't know. Some specification needed, but this is okay. Okay, so then the point is, if you pick the correct operator insertions, you can actually get QKZ in the standard form from account. And the which one? The no, but what, that this was somehow not complete, or yeah, no, it's just this is good in low energy, but you really want the one coming from the UV gauge theory, and so this some things which might be the same in here can be different there. That's all I'm saying. So in math, it just means like the more correct thing for the story I'm going to tell is really K theory of the ambient quotient stack, which is much larger, but somehow this subtlety I can mostly avoid. Okay. And so, I mean, these two people figured out that the correct operator insertions you want to use here are the stable envelopes. And then the kind of non-trivial statement here is that they actually exist for these varieties. This actually follows abstractly from the kind of most recent existence theorems for stable envelopes, but here we can actually write them down explicitly and show that they have this actual application, that if you insert a stable envelope here, you'll get a solution to QKZ equation from geometry. So I'll kind of briefly explain what that looks like, but I will be a little bit sketchy just to avoid getting too technical.
Before you do that, you get something stacky or
No.
not?
Forget stack. All I'm saying is the partition function by itself, some kind of interesting special function, but it's not the special function you want. It's not actually a solution to QKZ equation yet. If you want to actually get QKZ equation in its standard form acting on a function which carries an index that the QKZ operator acts on, you need to insert a stable envelope. And the stable envelope that was labeled by something, and that label will be the index that the matrix of QKZ hits. Okay, so just a brief review of, this is going to be extremely brief because I think a lot of people in the audience already know this. What is stable envelope? So it works in some level of pretty high level of generality, but in this case, it falls into this scenario where we have torus acting on variety and we have some subtorus, which controls this positions of punctures in QKZ. Stable envelope is supposed to give kind of a map. like this. And they're determined once you pick a choice of chamber. Inside of A, which you can think about as just like a choice of ordering of these parameters. Well, this is one, but in principle, it can be whatever you want. And so kind of the idea is that stab is supposed to be some kind of like refined version of just taking the structure sheaf of the attracting locus to, well, in general, F, or F is a component of the fixed locus of A. And so the reason you have to be sort of refined is because, yeah. This is T, so this is T. Yeah, now so I can briefly tell you what fixed locus of A looks like. Okay, but the point, it's not different enough from this to matter. Okay. Right, so it's some kind of refined version of just taking structure sheaf of the attractor. The kind of point of it is that, you know, when you actually look at like things that attract to fixed points, you can think of that as some kind of like space of gradient flow lines. And if you have many different fixed points, the flow lines can break. Right? And so you want something kind of that can tell when you've had actually a sequence of flows that takes you between various fixed points ordered by attraction. So the important thing is there's one stable envelope for each T fixed point. And the way to state our result is basically the following. So to each one of these, you have corresponding stable envelope. And then you can study basically this object, which is defined in a similar way to Z. But now corresponds to in here, instead of just looking at the character of virtual structure sheaf, if you want to tensor it with a pullback of stable envelopes under evaluation of 0. And now, I guess to avoid telling you like a complete lie, something, you know, whenever you deal with quasimap, you have to be careful with evaluation maps because evaluation maps, quasimaps in general, only go to the stack. But the reason that the formula I wrote is okay is because these, in some sense, extend canonically to the stack. So that's really the version you want. But anyway, and so this object basically is the fundamental solution matrix. I should say Z solution. To UH bar SL2 hat QKZ with n Verma modules. Yeah, okay, yeah. Yeah, like you have P over here, and then you have some insertion. Stab P prime. There. Oh, well, in general, I mean, you can think of it as like a cigar which is contracted to P. If you can put, so I didn't explain this because I didn't want to explain two things at the same time. But nobody forces you to consider boundary conditions in gauge theory corresponding to just approaching a vacuum, isolated fixed point infinity. In general, you can put something else. P. And so in general, if you put something else, it could be a condition where it sort of like lays in something, but doesn't necessarily just go to a point. Yeah. So the thing that, so here I wrote Z solution. So I'll briefly explain this point is that something which is unique to the world of Q-difference equations that doesn't happen with differential equations, that if you have an equation which is jointly analytic and two sets of parameters, in this case, they would be the Z's and the A's, the solutions will not be simultaneously analytic in those parameters. So here it's clear that because you've just written power series in Z, and this is the only dependence you have on Z, it's analytic. In Z, we're good. But when you actually write out this localization formula, A's are going to enter denominators in all kinds of ways. It's not, nothing is guaranteed nice about A's. But to get to the A solutions, there's some kind of transition matrix that you take some special linear combination of these, and geometrically this means you want actually elliptic stable envelope here. And that the elliptic stable envelope, its restrictions to the fixed points will be exactly the coefficients that will ensure that the poles cancel. Yeah. Yeah, it's in the KZ textbook. So in kind of first weight subspace, which maybe I'll spend time on. I don't know. You can write it fairly explicitly, and then there's some formula in like Clebsch-Gordon projectors that you can write for the.
There's been some kind of revival of the issue. We can just, but then Gordon followed up with this kind of, combinatorial process of this larger story. There are people. The look at kind of organization.
Oh yeah, I don't know. I also don't know that much about lattice models, so I'm not sure. It comes from this though, for sure. Okay. All right, so this is kind of the main technical result. Maybe, so depending on how people want to spend time, because I'm not going to try to break the time record. We can either discuss this in some example, or explain like applications to Langlands and knots. So, do we need an example, or was this kind of concrete enough? Applications? Yeah. So raise your hand if you want an example. Okay, we're doing applications. I should just mention, like one of the really nice things about working with quasimap is that there's actually some very explicit integral formula for this. I mean, you don't just have to think of it as so. I don't want to write that. But the nice thing is that the geometric techniques and language kind of work uniformly. Yeah. Well, that's what sort of, it goes back to what Andre had said in the beginning about like Reshetikhin's old idea is that you put kind of the off-shell Bethe wave function inside this integral. So if you write that as integral formula, that should be the insertion which solves QKZ, because essentially in stationary limit, QKZ will pass over to just the problem of diagonalizing spin chain Hamiltonians. And so, yeah, the stable envelope is sort of the stable envelope on the stack is a more precise way to say off-shell Bethe wave function, sort of like the best representative. But like philosophically, why? I don't know. Okay. So application 1 is to this ramified q-Langlands. Oh yeah, no, that's fine. Yeah.
Because like if I like to write the argument, it's so bad.
Yeah, yeah, like textbook formula, right?
That's not before.
Mhm.
It does mean that, but it's in this situation, it means that the molecular relation of actually what is about.
Yeah, so right.
If it doesn't work,
because that's like the advantage of stable maps is that always is that they still have the evaluation map because the curve just degenerates and moves them off to some place where they still can evaluate. But in quasimaps, curve is fixed. So if you want evaluation map to exist by the same mechanism as stable maps, you need to allow the curve to move. And probably so. I mean, since for this story, like since we already knew that somehow the descendant version worked, we didn't really worry about relative quasimap. But I mean, presumably you could do the same thing. Anyway. Okay, so this goes back to Mina together with Frenkel and Okounkov in 2017. And some kind of correspondence in general of conformal blocks between quantum affine algebra and these QT deformed W algebras. And kind of just the very brief kind of addendum that we can make here is that if you want to actually, so this is viewed as some kind of incarnation of Langlands correspondence. And basically the reason is because after various kind of degeneration limits, so like one degeneration limit is to where this becomes just affine algebra, and this becomes what's called usually W beta algebra. Sometimes people speculate about this and call this the quantum geometric Langlands. The motivation for that name yeah, okay. So okay. And the reason for this is that these further deform to when basically kappa equals 0, which is critical level. This is somehow like very singular limit of this. It corresponds to like in WZW models all the way back from the beginning. This is like infinite strong coupling. But this kind of becomes like this what's usually called classical W algebra, W infinity algebra. And so like in original like Valence and Drinfeld construction, these are things people tell me. My understanding is that the Fagan and Frenkel construct some kind of identification of the universal enveloping, the center of the universal enveloping algebra of this with this. And this is an important component of the original Langlands construction, and conformal blocks of this, and so critical levels, again, a very kind of special limit. So you have to be careful about what you mean by conformal blocks. But conformal blocks of this can correspond with the Hecke eigensheaps of Langlands. So then it's natural, like from physics point of view, don't go to critical level, just do, finite coupling. And the deformation of this to finite coupling and this to W beta should be some deformed version of Langlands called quantum geometric Langlands. And then because these both admit the Q uplifts, one expects the Q deformed quantum geometric Langlands. So it's usually called quantum Q Langlands. And the point basically similar to what I explained here was, just now, is that originally maybe we were motivated by KZ equation, but to actually get a nice geometric story, we want to sort of deform this to QKZ. And so likewise, to be able to kind of say these kind of dualities or correspondences more explicitly, you want to work in the most deformed version that you possibly can. And the point is that this thing you can actually, it's not just isomorphism, abstract isomorphism vector spaces, maybe not so interesting, but you can actually get a correspondence of basis vectors in these two spaces of conformal blocks. Yeah. So this is like Q to 1, and then you send H bar to 1 and T to 1. But Q is like H bar to the minus K, K is fixed. And then T is like Q to the beta, and beta is fixed. But anyway, so this is kind of the story from those papers. Now, the point of today is basically that if you want to include ramifications, it corresponds to these actually these Verma module type vertex operators that we were able to understand geometrically. And in some sense, like I think the fastest intuitive way to see this is to go back to what I was saying about Chern-Simons in the beginning, where if you want to have Verma modules in Chern-Simons, you really need to think about actually deleting something, right? And it's like finite size puncture in some sense. But sort of like the more technical reason is that, unfortunately, in SL2 you can't really see this, but for more general G, when you have Verma module complex highest weight, this can label the ramification types, because the most generic ramification is just like generic complex highest weight, but then if you go to like boundaries of wild chambers and stuff like this, you get other types of ramification data. So the point is that we can also establish the ramified version for now, just for SL2, by the same logic that was used here. And to recall that logic, the point was to think about the curve counts. And here I'll just draw the base curve. So I had explained that basically if you have a stable envelope inserted, this kind of thing gives solution to QKZ. If you have no insertion, that was a Nekrasov partition function, right? But in fact, this is also, and so of course, these are all going to I'm using just these as the shorthand for the partition functions of all accounts. This is the WQT SL2 block. Essentially, from integral formula, this is obvious, because this has free field realization, and the integral formula that you get from localization formula just coincides on the nose with the free field formula for this. Oh yeah, that's this cylinder that we have, punctured cylinder. Same as throughout. No, the P1 somehow auxiliary. No, they don't enter. The Langlands happens on here. I mean, so somehow. Yeah. So remember, this curly A is the curve on which the solutions to QKZ live. They depend on these variables. These other parameters that enter the counts, well, like from the point of view I've told you today, they're all auxiliary, but somehow, or they would correspond to like parameters in affine the algebra and Verma module highest weights and just details of QKZ on the curve. Like, if you embed this string theory, they all just correspond to some geometric background parameters basically. Okay, great. And so the point is that if you want to actually develop a correspondence between these type of things, is almost, the pictures make it clear an obvious proposal. It's just if you have no insertion and you have some basis of insertions, you can expand one in the basis of insertions. And so this works here. You can just write one as some linear combination of fixed points over stable envelopes. And basically, huh? Which one? Oh, yeah. If I want to parallel with all this stuff. Yeah, left-hand side is this, and right-hand side is 1. And so what that gives you is just by applying, like sort of taking this formula and inserting it there, you get basically something like quantum affine block is some covector times, oh no, I'm sorry, other way. Covector here, 1. Oh yeah, so somehow this is a little bit tricky. Yeah, just think of this case like structure sheaf. And so this is just explicit identification of space of conformal blocks. So like you can actually write some formula for this, you can actually write some formula for this, and then this to determine the explicit form of this guy is algebra exercise. Just yeah, so the covector is like the C's. So roughly, like remember the index of stable envelopes sort of labels like basis in the space where the QKZ operators act. So then if you want to go from that to nothing, you want to pair it with some covector, which in this case is the C's. And that just gives you something with scalar insertion in this. Yeah. And I should mention here, these are known to physicists. I mean, these are the difference between ramified case and previous cases. That these are the Q, in this case, Q-Liouville blocks with primaries. And again, the sort of highest weights of the primaries correspond to the highest weights of the Vermas. So some identification. Oh, it means, like something happening at a puncture. And so again, like what I was trying to explain is that if you have Verma at puncture, so it's a little bit hard to appreciate with just SL2. But if you imagine like you're doing like GLN or something, so that this is actually a vector, like the ramification type. So like usually in Langlands and related things like AGT literature, things are characterized in terms of like allowed poles of like Hitchenfield or something like this, and basically how generic you make your Verma module highest weight is basically like how generic you make your like parabolic. And so here with completely generic highest weight, this is like B, just generic ramification. And so of course in SL2, this distinction, it's not relevant, but there should be some interesting story in for beyond SL2, which I mean, going beyond SL2 should not be like super hard. It's just that there was already enough stuff, with SL2 with applications that that was fine. Okay, so this first thing, I'll kind of close with the last thing. No, well, yeah, Laurent polynomials and where? Oh yeah, so in general, CP will depend on some other variables, but the equations, the point is that QKZ will just map into some equations that this thing solves. And it's like, it'll be like scalar Q difference equation. Yeah. Yeah, probably. I don't think it was known. I mean, I don't know enough about Q-Leuven world to tell you if it helps, but I'm sure it somehow helps. It's better to have an equation than no equation. Okay.
Like the only you did to play well.
Oh yeah. Like you could solve by like pairing with the dual, and yeah, it'd be Euler character of the dual. Oh, I've looked at it in like really basic examples, but I haven't checked the formula if there's any. I remember, yeah, we talked about something like this. So yeah, maybe I should. Yeah. Yeah, no, what we're saying is somehow, like in the end, they're supposed to actually be equal. So what I'm saying is that if you start here with no insertion, you can just write no insertion in terms of those. And then you're really inserting the same thing, which is nothing. It's just that it gives the appearance of being non-trivial here. This is just like saying, like in abelian, like k equals 1 case. This is just saying 1 is a vector in a vector space of polynomials of degree at most n. And then if you pick some basis which is not just the monomial basis in that vector space, the coefficients will not be trivial, which to express, right? No, I think pretty much per definition, if you want to get W algebra block, yeah. Yeah.
And then you say, well, all the nodes correspond to you get an integral formula, say, all the nodes and integral formula here, size integral formula there. So it's like you took it apart and say, the string operator is equal to this is what really zero conversion, perfect operator, string operator. Like you're having all combined and integrated and
Yeah. Yeah, this has a big flavor here.
Right. So I was wondering, if you remember some ideas on the basis of power,
Short answer is no. I hadn't thought about it yet. But yeah.
My part of that story is that it's not like you kind of genetically realize just the end result. You also need to realize all the kinds of intermediate states.
Yeah.
You organize and have that only does the own result.
Oh, yeah, right. I agree. No, I haven't thought about that, but this is something that one could do. Yeah, sure. Okay. The other thing that I have thought about is this categorification of this FK guy that I talked about in the beginning. So this was kind of like a motivation to even think about this whole thing to begin with. And to explain the relationship between these two things, basically I just have to tell you how to go back from like quantum affine SL2 to just affine SL2. Because this is where the actual conformal blocks live, whose actual braiding gives you the not invariants that one was interested in the first place. So I should mention here that, of course, people think know that there are actually sort of two different degenerate limits you can take of quantum-affine SL2. One of them corresponds to Yangian, which is just like, trigonometric to rational, and the other one is, quantum-affine to affine, which is slightly different. And so this actually corresponds in gauge theory to the fact that 3D gauge theories have two different two-dimensional limits. And so this one, so this is 3D, this is 2D, this is like dimensional reduction. And this thing is some more careful scaling limit called conformal limit, just because you go from something without conformal symmetry to something with conformal symmetry. I should also mention this, this limit preserves Higgs branch, which is basically manifest from like quasimap counting, because this is the one which just takes K-theoretic counts to the cohomological. So you're just counting stuff in the same variety, which is the Higgs branch of gauge theory. This one preserves Coulomb branch. I will not have much to say about Coulomb branch today, but this is something interesting. And so what happens at the level of kind of base curve is up here you had the 3D theory lived on the sort of base curve times a circle. And then these two limits just correspond to setting the size of the circle to 0 while also like tuning parameters of the theory such that you sort of get something two-dimensional. And if you do this over here, the 2D thing you find has, you end up finding that in the interior, it has the A model twist. And on the boundary, it has B model twist. Or I'll say B model boundary condition. So it's like a cigar amplitude. And if you do the same, if you do this limit, your 2D theory has like B model twist in the interior and the A-type boundary condition. And so, these cigar partition functions will just be like, basically like Gromov-Witten type curve counts because you have A model twist in interior. These ones will be like some kind of period integral. And these are the period integrals which people here are very familiar with, because in our setting, what you get is L is some Lagrangian and Y, which will be symmetric, case symmetric power of a cylinder, and W will take some form like lambda, where lambda is related to Z. I mentioned it in the very beginning. It had to do with some highest weight of Verma on the boundary. Log Y plus 1 over kappa, sum over I not equal to J log. And so point is that you can now kind of follow the path which has been taken in the case of the finite dimensional modules, or really the minuscule ones, for the Vermas, and just try to use this superpotential on this space, because what you clearly have here is, if you were to actually view this more completely as the cigar amplitude, this is like cigar, which ends on the Lagrangian boundary here. And so what you're saying is the conformal block, this is a integral representation of conformal block, which comes from free field realization, is now coming from basically actual 2D Landau-Ginzburg model with some actual boundary condition. And so the point is that boundary conditions in two-dimensional theories are just automatically naturally objects of category. And so in this case, the category you want to use, and since it's an A-type boundary condition, is some type of Fukaya-Seidel category with this superpotential. Yeah. That has to do with the actual form this takes, because A model will localize onto the holomorphic maps, which is why it's what you, well, I didn't really explain anything about over here, but like a way to see that this has the A model twist is that the A model localizes onto the holomorphic maps, and this will still be some kind of you can interpret the result as integrals over moduli of holomorphic maps. B model localizes onto the constant maps. And so, of course, the two are related by just 2D mirror symmetry. I mean, it's almost a question of duality frame, but like, in some sense, it has to do with the form the answer takes. I mean, the cigar amplitudes in B model always look like period integrals over some Lagrangian. That's the fastest way to see. Okay. So the point now, to finish, is that we can use certain setup for computing FK. What with this potential? What changes the most are the gradings, because the gradings come from the like multi-valuedness of this thing. And so the main point is that here you want actually two variable series. And to see the second variable, you need some kind of extra gradings in here. And so the main point is that this coefficient, in the previous theory, yeah, maybe I should have emphasized this more. In the previous example, this was just 1. Okay, and it's just 1. Whereas here, keeping it generic and complex corresponds to keeping the parameter that you need to be able to see FK. Yeah. Okay. So at this point, we can use a sort of formulation of FK that was explained by Sung-Yuk Park, which is basically that if you take FK, there's going to be some kind of prefactor, which depends, it's just like simple function of Q and X, but it is mostly determined by a sum over all weight subspaces. So maybe to be consistent with my earlier notations, I'll just keep calling this small k, q to the minus k, trace of a braiding matrix acting in k. And to explain this formula, the meaning is, so any knot you can present as this kind of Markov trace of some specific braid. Oh yeah, so sorry. FK is capital K. I'll just call it W. K is for the knot. W is just for a weight subspace. Yeah, K is a knot. And I'm presenting it that way. Yeah. So Q is the same thing it always is in knot theory. Like in Chern-Simons, it's that. And then X is roughly Q to the mu. Where here relative to this, I can in principle have, in principle you can, but that corresponds to like having a link. If you just want, but if you just have like not, they're all just equal to the same thing. So yeah. So relative to what's up there, mu1 and mu-n all just coincide with mu. Okay. So you kind of have to use this. So to say like, what is the idea here? It's that when you have the Verma modules, you have to be careful about actually defining what FK is, because they're infinite dimensional. So if you do something kind of too lazy, it probably won't converge. And even this requires still some care. But the idea is they're sort of naturally stratified into finite dimensional weight subspaces. And so if you have like n, so here n would be 3 punctures, then you look at tensor product of 3 Verma modules, you restrict in each weight subspace some level below the highest. So yeah, maybe I'd say BW X in nth power here. And it would just be n minus 2W. Yeah. Oh yeah, so this is braiding matrix. It's going to be made of like a bunch of R matrices that depend on Q and X. So like if you had some explicit picture here for B, like I don't know, something like this. You know, here you would have n equals 4, and for each crossing you would get an R matrix. And if you restrict to some fixed weight subspace, it's just R matrix acting in that weight subspace. Yeah, it's just trace. Oh yeah, yeah. So the idea that is that it's not guaranteed that this converges sum. I mean, I think strictly speaking, if you want to be like totally precise, it's for some like known but large class of knots. This is okay. But in general, it's not there's no a priori like proof that it converges for all knots. But this is good operational definition.
So we're saying so W is the number of strands.
No, oh yeah, for you it's the number of strands, right? It's the number of it's what I was calling K here. I just switched it to W because I'm also using K for the knot, so I didn't want to create. Yeah, actually, yeah. So we Z2.
So it's just like thing that gets off of B acting out some of a greater like
Yes.
all the possible weights of the
Yeah, and so the idea is basically to sort of cut to the point. The conformal blocks, which come from these kind of period integrals, are you think of as coming from two-dimensional Landau-Ginzburg model with this superpotential. And so the trace of the braiding matrix you can also engineer from Landau-Ginzburg model, and what it corresponds to is some kind of torus partition function. So it's like you have Landau-Ginzburg model, looks like this, and then you somehow put like it's on torus, and you put like a twisted boundary condition by B. So to explain this picture, like your variables are like functions of S and T, where S and T are just coordinates on torus, and you impose that like y of 1t is I'll explain the notation in a second, by beta y of 0t. And so the point is that whenever you have a braid B, it induces symplectomorphism of y, which just moves punctures basically. So why? Oh yeah. No, trace of B converges. It's sum over weights that you have to be careful. That's all I'm saying. This is usually what people call quantum trace. It's just this.
No, I think the problem with sum. Yeah, the whole sum doesn't converge. The trace of B for every.
No, yeah. For every W, trace of B is just a finite sum. I mean, so that's fine. It's just the question of if you basically lose control of which powers of Q show up, then you can run into trouble. But like,
there's nothing to trade that with.
Yeah, but all I'm trying to say is you can compare the actual values of the congregation. You don't need to the trade.
sure. Oh yeah, but so you see somehow.
If you're somehow not now,
No, I agree, but somehow the reason we want trace is because if you try to follow literally the path that was taken before, that this requires you to use these cups and caps. But the existence of those for Verma is at best not clear. It's somewhat, yeah. Yeah, no, like I've calculated some Euler characters, and yeah, you can get matrix element by matrix element. This thing. It's just for this for the statement of today, I'm just going to be lazy and work with trace. But you can get matrix elements, indeed.
there's a two Torus picture, like there's a B drawing.
It's not a very good picture, but what it means is, so it corresponds to closed string theory and what's called twisted sector. So it means that if you think of this as like closed string partition function for closed string propagating around this way, basically when it comes back, it doesn't have to come back to itself. It can come back to itself after braiding. Yeah.
They correspond to when you rather than all the characteristics are not. When you cut it open, you get the home.
Yeah, and so in this case, if I cut it open, the way you want to cut it open is here. And at the like fixed slice like this, you see strings with the kind of twisted boundary conditions.
So you have two Torus, and you pass the two Torus along the circle.
Well, what I'm saying is like there's just this distinguished direction, Torus, right? This one of these directions, and your fields are basically maps from Torus into capital Y.
Okay.
And now what I say is that when I go around in this direction, they're not actually, well, so not like actually maps, but they're somehow twisted.
Somehow. Yeah. So what is phi beta?
Phi beta, so the braid induces some map from Y to itself. Like if you want its action on T brains, then it's just the one that moves the. Yeah, right. Anyway, so the point is that just like what Mina was explaining, if like the decategorified version of before was some kind of annulus amplitude, here it's some kind of torus amplitude. So if you cut open, the proposal for categorification is just the vector space of ground states that you get from quantizing closed strings with twisted boundary condition here. And if you sort of go through the details of Landau-Ginzburg model in this context, what you find is it corresponds to something known in math, which is called symplectic floor homology of this map. And so the way this is defined is that it can be defined as the cohomology of a complex. To avoid going over, I'll just keep this kind of vague. It's just like Holmes and Fukaya category. You start with some complex of fixed points, then you count disks to eliminate the fake ones. So here, what you do is you start with a complex of fixed points of the map phi beta, and what you count are sort of cylinders that interpolate between two fixed points of this map. And so now they're not like exactly cylinders because of this kind of twisting, you have to think of them as, in some sense, having a branch cut. So you can formulate this precisely by saying that there's some kind of mapping torus. And if you take mapping torus times R, this projects down to C star, and then you count holomorphic sections of this projection. This gives you HF. Now, to cut to the point, this can be identified with basically Holmes and Fukaya category of two copies of Y from the diagonal to identity, basically just the graph of this map. And
Okay. How does all these previous story?
yeah, so it's the previous story came from before we took that limit. The previous story was about quantum affine symmetry. This story is about just affine, just affine Lie algebra from conformal blocks. So somehow what happened was we had some three-dimensional n equals 2 gauge theory, which is quiver gauge theory based on the quiver that I wrote. And then when we took this specific two-dimensional limit of it, it became a Landau-Ginzburg model with this potential. Okay. And then the claim was that because I knew how to get Q-deformed conformal blocks in three-dimensional gauge theory as just corollary of that, I could get the two-dimensional conformal blocks. I'm sorry, the honest conformal blocks, not the Q-deformed ones, and the conformal limit. Once I know that I have a Landau-Ginzburg model which computes for me conformal blocks as cigar amplitudes, categorification is obvious because you just take category to be category of boundary condition. So anyway, the point is that then the proposal is that basically this thing categorifies trace of braiding matrix. we can calculate, it's current. What would be great is if we had some way to resolve diagonal that worked uniformly so that you could actually compute these home spaces. We can't do that, but we can check Euler characters for sure. And we've done that in a few examples, well, several examples, and it works. In fact, it works even better than trace. You can get braiding matrix elements on the nose. Y is like downstairs Y space.
What's the answer?
I wish I knew. Basically, presumably, what should happen is so you can see just by matching B's and A's that these two things are exchanged by a two-dimensional mirror symmetry. And the statement is that if you have a pair of 3D mirror theories, this limit in one of them corresponds to the other limit in the mirror one. So essentially, if one could write down the 3D mirror for the n equals 2 theory that I was studying, that would give you the B side in that limit. But it's somehow not immediately obvious how to do this. Yeah, I won't say anything else about that. But I definitely am interested in that. That would be really cool. All right.